Hi, so I wanted to get the talk started. I want to introduce Professor Bob Brodersen, who is my thesis advisor and it's a very special part of my life. Bob is a very distinguished professor at UC Berkeley. He's a member of the National Academy of Engineering, many awards, been a professor since the mid-70s, won an award for a top 10 contributor over the past 50 years to the ISSCC conference. But an amazing statistic that Bob told me a little while back is that he was looking over his statistics or whatever and found that he had over 150 graduate students, I guess, is that master's and PhD over the years. And I'm very proud to say that I was one and wouldn't be where I am without him. So here you go. Thanks, Bob.
Thanks a lot, Hi. Right. Appreciate that. Well, okay, so what I'm going to try to do today, I know Google is not one of the big high volume semiconductor operations, okay, so it's a little bit different take usually people I talk to. But I guess what I really want to try to show you today is I think what's really going on in sort of, where, computation's going. And so that's kind of what the story is all about today. And I'm going to start off with actually some sort of background on sort of architectures, okay, so, what makes something be very efficient, okay, and clearly, I think one of the big numbers right now is power efficiency. I think it's a problem you might probably have here. It's clearly a problem that's in the general purpose computing world right now. I mean, Intel could make faster processors if they weren't power limited right now. So we're in a power limited regime in computation. So how do you deal with that, and why is it a problem now? So this is actually a chart I did a few years ago, but it's really interesting. Okay, so let me just kind of walk you through this, what this is all about. The chip number thing at the bottom there is actually, it's connected to actual designs that were done and published at ISSCC that had all the information that I needed to do this chart. The axis on the other side here is energy efficiency. Now this is millions of operations per second per milliwatt. Now that's two rates, one over the other, right? So that's really an energy efficiency number when the time gets sort of canceled out. So it's actually energy per operation. Okay, so if you think any function you have to do has so many operations it needs to do, okay, well, you can figure out how much energy it takes. That's kind of the fundamental thing you have to sort of worry about when you talk about how much power it's going to take. Okay, now, as we go across here, I have three basic groups: microprocessor, general purpose DSP, and dedicated. And as we go across this, what we'll see is that the numbers go from 0.1 for the microprocessor, and these are Pentiums, Power PCs, those are what those chips really are. I mean, I can give them to you if you're interested. You go to general purpose DSPs, and these are these DSP chips like Texas Instruments makes and other places, right, that have some level of parallelism. It's beginning to dedicate it to a given function, okay? And then there's these dedicated chips on the far end over there, okay? Now notice the range. We go from 0.1 for microprocessors, Pentiums and so on, up to 100, a couple of hundred for the dedicated chips. And this is actually a couple of year ago slide. Actually, the numbers now are actually, I think the spread is even more. That's a factor of 1,000. Okay, 1,000. So get that in your heads here, right? I mean, we all know that dedicated chips that we do are a lot more efficient than something that's general purpose. And a big part of it's because of the flexibility you have to put in. But the number that needs to get in your head here is it's a factor of 1,000 potentially, okay? Now, intermediate positions like these DSP chips of TI are 10 times or so better than a Pentium, and that's why TI can make a big business out of this stuff. But we're still a factor of 100 less than this dedicated stuff. Okay, so here's the question. What's going on here? I mean, this underlies the real argument. If we can understand what architecturally is allowing these dedicated chips to be so efficient, maybe we can begin to use that in some sort of general purpose environment so we can really have a much better efficient solution, something to replace effectively the Von-Neumann architecture. Okay. So let's look at three chips, and I'll do this pretty quickly. One's a Power PC, one's a NEC DSP chip, okay, and another one will be sort of a wireless LAN chip, probably wireless LANs like you're probably using here. Okay, so this is a sort of just three examples, and we'll look at those and see what's going on in those three, the architectures of these three chips. So we start off with this Power PC thing. Runs about, this is a few years ago, so it's running about 500 megahertz. It only can do two things at a time. It has an integer and a floating point unit, so it can do two operations in each clock cycle. So effectively it can do like 900 MIPS, and I kind of roughly let MIPS be equal to MOPS, which MOPS being an operation. Okay, so basically we're talking about 900 MOPS of performance. It takes about 7 watts, and you can take that ratio, and you get this MOPS per milliwatt number of 0.13. Okay, this was the best of the power, best of the Von-Neumann classical architectures, you know, in the quarter micron technology that these chips were all common. Okay, let's take the NEC DSP chip, and let's look at it for a second. Okay, MOPS, there it has 4 parallel DSPs. Now this is, okay, and inside each one of those DSPs, actually, there's 4 operations could go on, because they pipelined it, and so they sort of allowed that to happen. So you basically get 16 operations per clock cycle. The clock rate drops, actually, down to 50 megahertz, but you still get 800 million operations per second. So it's the same as the other, but it's only 110 milliwatts. Okay, dropping the clock, okay, has some big repercussions in how much power it takes, and particularly it has repercussions if you can fool around with the voltage. But so you get a factor of 7. So this is factor of 10, better than we got with the PowerPC. What was the key thing that happened here? It's not that we dropped throughput. We still have the same throughput, but what we did is we allowed ourselves through parallelism to be able to drop the power consumption. So this is fundamentally what's behind it. It's looking like parallelism is the way to make this thing go. And we see this happening with Intel. Intel, after fighting parallelism tooth and nail for so many years, right, finally has decided, well, we can put down 2 cores on a chip. Okay, right? Breakthrough. Yeah, right.
I mean, a large chunk of the actual layout is used for cache
Memory.
And that's not present here. How much is that affecting us?
Memory is actually a really interesting thing. You say, well, geez, you know, most of the chips are all just memory anyway, and the little small part's just the processors. Why you worry about the processor part? The reason it's the architecture that really does that. Think what's happening. You got this little, you know, the processor unit, okay, which is running faster and faster. What do? You have to queue up intermediate results to feed that the processor part of the thing. So as the clock rates go faster and faster, if you don't have parallelism like this, what you have to do is you have to store all the intermediate results to be able to feed them down into the processing unit later on. So in fact, it's actually a failure of that architecture, which requires more and more memory as you try to speed things up more rapidly. Here you have less memory because you got more processing units. The data is actually closer to the processing units, and so you begin to don't have that bottleneck going into memory. So that's really actually a part I'm not going to talk about, but really another fundamental flaw in the whole von Neumann basic architecture. So let's go to the last one. This is the dedicated one. Okay, now this doesn't have any flexibility or very limited flexibility, but the numbers are interesting. Okay, so this is a 802.11 chip. Okay, so this is, you know, might be in your laptop. Basically, it has 500 things happening in each clock cycle, okay? The clock rate's only 80 megahertz, but you get 40,000 million operations per second on that thing, right? You divide those 2 numbers out, you get this MOPS per milliwatt number of 200. Right now, in 90 nanometer technology, that number is actually around 2,000. If you do something really dedicated, you can get 2,000, you know, MOPS per milliwatt. Every milliwatt, you can get basically 2 billion operations per second. Wow. Huge improvement, you know, incredible efficiency. Why is that happening? It's because of this incredible level of parallelism that we have here. So that's the key. Now, what made this one so good was it's heterogeneous parallelism. It's just not parallelism. The problem is if you start putting down a whole bunch of cores, it's hard to figure out how to partition your design or your algorithm, whatever, to sort of fit into this homogeneous parallel architecture. If you have the freedom to sort of do anything you want, just put down the parallelism that exactly fits what your problem is, and if you're able to do the communication between it, and if you're able to put the memory where it needs to be to sort of feed those processing units, then you can exploit this level of parallelism. But that requires things to be heterogeneous. So that's a big difference from what we've been talking about so the Intel model, putting multi-cores down, okay, that's homogeneous. Now you've got a real programming problem to figure out how to map your algorithm into that homogeneous basic parallel structure. So the bottom line is we want to have heterogeneous parallelism with dynamic, basically, communication with distributed memory that we can put where we need it. How do you do that? Well, ASICs do it, but they do it for one application. Okay, so that's nice, but probably not what's interesting here. Okay, field programmable gate arrays. That exactly is what they do. Okay, what a field programmable gate array is, it basically uses ASIC-like architectures, dedicated chip architectures, but it gives you full flexibility in interconnecting these things up. You could make a Pentium out of these things if you want to. You could make a PowerPC out of an FPGA, no problem. There's overhead because you're not sort of, you don't have designers going in there and optimizing every wire you have. But the bottom line is you have full flexibility to put down the parallelism that just as you need it for your application, and you can change it. And you can change it in about 10 milliseconds. So you actually cannot just have to do it once. You can sort of change it as demanded, as needed. Okay, a different process comes in, you can change it. Really key part of this, FPGAs weren't very interesting very many years ago. 3 or 4 years ago, maybe, FPGAs didn't have enough capability. They were kind of logic replacement things. The thing is, you think about what happens to scaling. Scaling does, it allows you, as you scale down by lambda, the size of the minimum dimension, the number of things you can put down goes up as lambda squared, okay? FPGAs just exploit that fully. So what happened is FPGAs just, in the last few years, went past the computational capability of the best microprocessors, and even the multi-core thing. So what's going to happen? It's going to get better rapidly into the future. So this is the technology that's actually fully exploiting all the Moore's law capability of our scaling we have. And you don't need to do it with high clock rates. That's the key. Because this really supports multiple high levels of parallelism, like I showed in that 802.11 chip. That's the kind of architecture you use here. You put down the parallelism exactly, it maps to the algorithm you try to do. Okay, FPGAs, where do they fit now? They're not as good as the dedicated chips, okay? They're certainly better than any Von-Neumann processor, or even multi-core Von-Neumann processors, right? In actual fact, I should just say something. When you put down multiple processors, okay, and just put them all in parallel, you actually don't improve the energy efficiency, right? Because you double the power and you double the amount of computation, those two things divide out. So you do not improve energy efficiency. So by putting lots of parallel cores down or using lots of parallel processors and some sort of network of workstation strategies for getting a lot of computation, you're working down at that 0.1 MOPS per milliwatt energy efficiency. Very, very bad. So you got to change the fundamental architecture to get yourself working up at a different level, okay? And the big advantage, just interesting to you, just one second, I'll say something here. This overhead is large. 95% or more of an FPGA is in the interconnect, okay? You think, wow, that's really bad. But you still come off, factor of 50 to 100 times better. Yeah, question?
So the data point used for FPGA, is that from the L2.11, or if you use FPGA to make a Pentium, is that data point still valid?
Okay, so this would be, that data point right there is from Xilinx chip. Okay, the question is, what's that data point correspond to? What's the architecture behind that data point? And the architecture behind that data point is the 802.11-like heterogeneous parallel architecture, maximizing using all the possible parallelism you possibly can get on that FPGA. Okay? Yeah.
So often the microprocessor is used for like a database join, a very data-intensive operation. You sort of allow you to do a little bit with each piece. Whereas the ASICs and DSPs are more like doing lots of operations on one piece of data, right? Can you get those benefits on operational database where we have lots of data doing sort of limited by that?
Okay, I think I got your question. If I didn't get it right, let me hit me again, right? What the right architecture for this stuff really is a streaming architecture, actually, if that's what your conclusion was. Because that is what these ASIC architectures really are. You stream the data through, processing's going on at every different part of this thing. It's all done in parallel, right? You can have multiple streams going through this thing, and you can manage the communication to the memory and the storage that you have as needed because you can put it in the communication links. So that's the perfect architecture for it. So if that's, is that what you meant? That was the question, basically?
The question is, what if you haven't got much to do per data element?
If you don't need to do much computation per data element, then you don't have a problem, seems like, right? I mean, I guess the problem is, this is for getting high levels of computation and high levels of memory bandwidth and high levels of disk bandwidth, too, because remember, you're distributing everything. So if we forget about computation, we just want to get I/O bandwidth, wow, this architecture is just perfect because you can just put up as many parallel paths, ports as you want to inside bringing data in. That, to me, seems like not knowing the Google search problem very well, but that seems to me the key problem you guys have. It seems like you've got huge amounts of memory, and you want tons of ports into that memory to sort of be able to do relatively small amount of things with it. Let me tell you, this architecture supports that very well as well. So, and I'll show you what our basic machine we're building, how it does that. Actual chips, well, things are getting better and better. This is just showing the scaling thing I talked about. These are figures of merit, but bottom line, these plots here, the bottom line there is MOPS per megahertz per million transistors. Just shows the efficiency of the basically Von-Neumann architecture just getting worse and worse over time. FPGAs in that figure merit have been staying constant. And so it's basically, it's sort of scaled to how many transistors you have, so it sort of takes the fact that you can put more transistors on a given chip out of the picture. This other one here is another one is just how this raw capability on a chip. And that's what I said would happen not too many years ago is suddenly you can do more operations on one of these FPGAs than you can do on the fastest Pentium or any Von Neumann machine. Okay, that's hardware. Okay, so we figured out really good. Okay, heterogeneous architectures, we got a way to implement them using this FPGA technology. How do you program it? Okay, and this has really been pretty much the stopper. Okay, what happened is this FPGAs have been the realm of hardware, gurus in some sense. People program these things sort of like when they build an ASIC. What's really going on here, I'm telling you now, is the capability has gotten so high on these things that you no longer have to work down at that very low level, okay? That's the mindset you got to change, right? It doesn't need, we do not program this thing at the hardware level. We should not program it. It's kind of like you don't program a processor at the assembly level or at the machine level, okay? We can move up. Once you begin to move up, you could do that when there was enough capability that you could sort of waste some of it, okay? And that's what's the situation with FPGA. So we got to move up to a higher level of abstraction. So when we program this thing now, that we can get people who have real applications to actually use it and not have to be bottlenecked by trying to have this thing programmed in some hardware description language, okay? So there's the change. This is critical. Two things we need. A, we need parallel algorithms. We need to have multiple paths to get in. We have to take the architecture and get it away from a sequential description because if your description is sequential and you stick it on an FPGA, you're not going to be able to exploit all the parallelism. So you've got to have a parallel algorithm. And I would guess the Google problems are very parallel. The second thing is you got to have a language that supports that parallel description. And that's really what the problem is. If you try to stay in C, you got a sequential description at your core, it's going to be really hard to figure out how to make that thing parallel, okay, right? And that's been a failure of forever to try to figure out how you take parallelized C or a sequential description. People come up with all sorts of solutions of that. There's a lot of different ways of going at that. Of course, it's the problem on the table right now, and as we move to multi-core technology, we're going to have to sort of explicitly deal with multi-threading is one solution, but it's going to have to be lots of other ways. We're going to have lower levels of exploiting the parallelism that's available inside future generations, because parallelism is going to happen. The question is what kind. A bunch of different languages to do that. We actually, because we came at this from a signal processing background, so this is a little bit different from what you guys do. But I'm going to follow that path down just for a little while because of the success it's had in being a general purpose computing environment or general purpose language. Even though it's driven from MathWorks, MATLAB is what we use basically, and it's a graphical language called Simulink that we use. We're using it for all sorts of stuff, okay? And stuff like circuit simulators and biological search problems, okay? And so even though it may think, well, geez, that's just a DSP thing, actually, people use it for all sorts of other stuff. Now, there's probably better languages. I'm not sure what they are yet. Okay, maybe some ones I just shipped there would be some examples. Okay, so what do we have available to us? We have a way to describe control. We got a way to describe data paths, and we got a way to describe. We can basically build up higher level macros that people can sort of program in. So it's basically a graphical programming language that you can extend, and it has the basic idea of control and data path and communication. Explicitly, basically, what you do is you put down blocks. They could be memory blocks, they could be control blocks, they could be data path blocks, and you hook them up, okay, right? So it's a data flow-like description. So that's why I said streaming is really the core way to think about this thing. I mean, what goes across those lines is data words, okay? They move across those lines. You'll pipeline this thing to sort of be able, if you want to have these multiple things happening in parallel, or you can have you can parallelize this in other ways, okay? So this is a DSP-like thing, but I think if you can see there, all the fundamentals are here to be able to program anything you want in it. And I'll show you some examples of how people are using this, and you can sort of see, I think it gives you some insight that you probably could program your problems in something like this language or some other language that might be better. Okay. So here's just a design example. This is kind of what it looks like. We actually build out of a library of blocks that actually are optimized for Xilinx, okay? And these blocks are multipliers and adders and registers and stuff like that. So it's fairly low-level stuff, okay, right? You can build up out of bigger things, like we can do for our signal processing world. What we do is build like FFTs or Viterbi decoders. Okay, we could block those up. Now you might have other blocks that you might want to program up that you would then use as your basic, building library that you could then build on top of. Doesn't mean you have to do everything graphical. The key thing about graphical is it explicitly puts in the parallelism, okay, because all these blocks are executing in parallel. It's the hardware execution model, and it shows you how the data is moving through this thing, right? And how you can parallelize memory coming from or data coming from memory. So having the ability to explicitly define how the communication works and how to explicitly show the parallelism is, I think, key parts of any description you end up with. This is one, but there might be others. This is a way to try to abstract this even more. I'll talk about this project. It's called RAMP. It's an interesting project. We talked about, that point that I gave, was that an implementation of a Pentium, or was that an implementation of some really highly optimized architecture for the FPGA? There's a whole group of people across all the top universities in the country right now that are trying to go after the multi-core problem. Okay, but I mean, basically we're talking about thousands of processors. How are we going to program that? How are you going to work with it? What's the message passing architecture we're going to use for that? Okay, big problem. So what's happening is MIT, Stanford, Berkeley, everybody's decided, let's get a platform to work on and sort of work on this problem and all the issues that have it. So in order to work together, the idea is we'll have big blocks, we'll have communication between these blocks. In order to share a thing, we sort of have this sending, receiving, and channel idea, sort of in a language that supports this, they have people work together. So the reason I bring this up, because I think it's these kind of ideas that are going to get us how we're explicitly showing parallelism, we're explicitly showing communication. It's this kind of stuff that's going to bring it to applications like you guys probably have. I mean, it's not going to be coming from Simulink probably, it'll be coming from something closer to this. But let me show you how the excitement of this kind of use of these FPGAs for actually trying to solve the problem of what multiprocessors look like, because you could implement the multiprocessor systems on the FPGA arrays. Okay, so let's talk about the arrays. We talked about one chip, we talked about a programming model, or the cores, how you might want to do it. What are the hardware requirements we really want to have? Okay, we want a reconfigurable platform that's more than one FPGA, because we want to scale this thing up. We have to connect a bunch of these things together, and we need lots of I/O. I think most of the problems we look at they get interesting because there's so much I/O associated with them. So here's the basic computing element we work with. Take one of these FPGAs from Xilinx. Okay, you can program this thing to do anything. It's got computational logic blocks, and you interconnect this thing through a program strategy that you just program all the communication links. This one is 130 nanometer. This is actually a couple of generations old. This thing has 70,000 logic blocks, has actually 2 PowerPC cores on the chip. They're actually a very small percentage of the chip, okay? It has 300 multipliers, 5 megabits of SRAM. What we did is we took that and we put around it basically RAM, okay? So I think it's like each one of those chips can have up to, I guess, 8 gigabytes of memory we can put around each one of these chips. We have a memory bandwidth of 12.8 gigabytes per second, okay? Each one of those chips has 23 gigabit per second serial links. Each chip, now remember that now. So here's the huge amount of I/O bandwidth that you have off these chips available to you. There's 1,000 pins on this chip. And this is, I say, a couple of generations ago. So there's huge I/O capability that you can connect to memory, you can connect to wherever you want to connect it to. Now this is the basic unit. What we do is take that basic unit and hook it together. Now you can do this a bunch of different ways. Our idea was, let's just make it look like a bigger FPGA and make it so it scales to even bigger ones, okay, right? So we have 5 of these things around. There's a lot of local communication. Each one of these units I show right here basically have the memory hanging off, you can see down there. Plus you have these 40 gigabit per second worth of these serial links that can connect to other things like other boards. So we got 5 of these things, okay, on one chip. Then you can connect through these serial links to other boards so you can scale this thing up. And you can put this thing in sort of a trees network, okay. You can then, what we do is we have 10 gig Ethernet switches that we can sort of crossbar and connect these boards together any way you want to. So this is the strategy to move this thing up to supercomputer level performance, okay. You can put storage off this thing. You can go through these crossbars, and we use InfiniBand or 10 gig either. In the future, probably even faster. So this is what one of the boards looks like. Okay, this is it. Each one of those chips, can consume up. I think the board, when fully, everything running on the board, you know, and mostly it's memory, the memory takes a lot of the power, is like a couple hundred watts. But the computation you do on a couple hundred watts, and this just shows the I/O. You got just 10 gig Ethernet. We actually put off HDMI so we can look at high definition video off this thing, and you know, we got all sorts of other stuff. So that's basically what it looks like. That's the hardware part. Now, you think about, and I think it's in some sense what the Google architecture is, right? Lots of, you know, general purpose commodity microprocessors sort of hooked together in various ways, okay? Yeah, that's a good idea, right? I think that's fine. The problem is the core element you're using is the wrong one because it has such low energy efficiency. That's the problem, right? What you really want to do is you want to have the core element based on these reconfigurable units and configured in such a way that you get these energy efficiency numbers that I've talked about, right? So this is the old way of doing supercomputers, right? I think the way you want to do them now is you take boards like I just showed you, you hook them up through very high-speed interconnect. You basically are able to exploit the available parallelism on each one of these boards, okay? And that's going to take, you know, algorithm work. That's, you know, you guys are probably the experts in. What we're doing is we're building these things up right now, and we can see that we can get up to sort of peta-op kind of performance on these things. Xilinx is very interested in these projects. They give us the chips, which is kind of fun, right? And basically, these chips aren't cheap. That's one thing good going for Xilinx here. These babies cost, you know, a couple $1,000s a piece. Doesn't mean that has to be true forever, because Xilinx has got a really good thing going for it. There's not much competition, right? And plus, the other thing I should mention about that, Xilinx designed their FPGA architecture thinking not at all about general purpose computing. They thought about this as sort of logic replacement. What's really interesting here, the technology just made this actually architecture not optimized for this application, viable for this application. You think, what happens if people start to think about, well, what we're really going to use this thing for is general purpose computing? You would do things probably differently, right? So I think there's just another factor of 10 or something sitting out there. Just people have to start working on the problem and think about how to use them for general purpose computing as opposed to what they initially thought about. So how can you scale this thing up? You make racks of these things. I guess it's getting like your guys' stuff, right? And so basically, you put these things together. You could put memory off this. So I think, and I say through these incredibly high-speed serial links that are available on these chips. I mean, 20 of these SerDes links per chip. Okay, you think about, geez, how you can configure this in many different ways. So I guess basically, this is getting some numbers in this thing. We actually sort of tried to figure out, you know, if you try to build a supercomputer right now and actually and do floating point, okay? Forget about trying to do fixed point stuff. Let's go after the supercomputer guys right at their heart. Let's do floating point stuff, okay? You can do it just fine in these Xilinx chips. So I'm telling you, so things are changing here with this technology, okay? Now here's a problem. We generally sort of, our old way of programming these things was we would sort of do a software, you know, this Simulink model I told you, this MathWorks thing, we would, you know, sort of debug our algorithms and then run it on a Von-Neumann machine, you know, our fastest PCs, whatever it could get, right? To sort of debug the algorithm, then we would download it into the FPGA. The problem is, we start getting big problems, the 6 order or 7 order of magnitude different in time between what it would do on our Von-Neumann machine versus what it was going to run on the FPGA mean we could not debug the programs, right? So you have to debug the programs on the FPGA array itself. Well, that's kind of, you start thinking about this thing as a general purpose computer, sure. If you've got a really fast computer, you don't, you know, do all the compiling and debugging on some slower machine. In fact, compiling for these things, what's that all about? Compiling for these things is place and route, in effect, right? That's really what that's all about. That's really slow on Von Neumann machines. We've got to put that on FPGA arrays to run them there as well. And that actually is a nice parallel problem, and it actually doesn't seem that hard to do. And that's got to be done. So there's lots of things you have to do to turn this thing into, so we have a software in, you know, sort of experience, you know, like we do with a Von Neumann architecture. So what we do is we say, okay, let's go after this problem. So on the left here is basically the old software approach, you know, basically design, you know, basically OS abstraction of the hardware. The old way of doing FPGAs, you had a big bunch of just low-level hardware CAD tools right in the center. They're just a pain to use, okay? And so that's kind of what everybody thinks of when they think of FPGAs. Well, let's abstract that. Let's do the same trick. I mean, you don't have to know about the internals of the hardware. You could abstract it away if you're willing to throw away some of the performance. You don't need to get every last bit of it. I should say, we never program these things up to more than 75% of their capability, because once you do that, you start getting in place and route problems, actually things slow down. So just throw away 25%. No problem, because you still got, you're ending up with these sort of TeraOp level performance. So basically what you need is an OS level that's living on that array, and it's distributed. It lives on each of the different processors. There's maybe that architecture I showed you, we put the control FPGA in the center is the one we communicate to sort of program these things. So we actually use one of the Power PCs that's sitting on that internal one, and we run Linux on that, and so that's how we get sort of communication in and out of the FPGA array. So actually, you log in to our board and do the processing there, and actually we can run the place and route tools on that Power PC, but they're pretty slow. But actually we can sort of just get rid of the Von-Neumann machine, well, get rid of an external one. We have the ones sitting on the FPGA itself. But I think in the future, as we start changing things, we'll put all this stuff inside, the array itself directly. This is just more abstraction of the hardware, or of the software flow, so it makes it look more like, a set of GNU tools and programming this thing and using it. So, and we're debugging it. Since it's a graphical programming environment we're using now, we're putting debugging in. So it's kind of like doing a -G option, right? So you'll slow it down, we'll put in things to keep track of what's going on, we can do breakpoints, we can stop it, Basically, we got to make these things, debugging this just like we would in a software world. We don't want to think of this thing as a big chunk of hardware. We can debug in runtime. We can sort of, there's a bunch of ways we can sort of, deal with this, upload stuff. We got so much memory available to us. We can sort of just basically capture traces and sort of follow through what's going on. So you can sort of see, man, this is kind of clearly not a solved problem yet, right? We're sort of thinking about how you might all do all this stuff, but you can sort of see where the problems are. To take this problem and turn it into a software problem, not get away from thinking of this whole thing as just a big chunk of hardware, which people did with Von-Neumann machines a long time ago. This BOS thing was what we did. We have Borth is what the student calls it, and that's kind of fun. I mean, basically what you can do is you log into this and you view the FPGA just like a file system. There's memory all over the FPGA. We do file system calls into that. We have a standard in and standard out that actually interfaces with the hardware. So we're beginning to break the line down between what's software, what's hardware, and certainly the user should never know what the difference is, right? Just that once you do certain things, boy, this thing runs really fast, right? Okay. So we started doing this stuff. We've been working on this project, I don't know, basically 5, 6, 7 years. And we could have, there was a B1, this is the B2. When the B2 began to happen, more and more people got interested in this thing. So we got a whole bunch of different people that are interested in this now. And I think this is kind of, there's no one doing Google search algorithms, that's for sure, right? But the point I want to make here is that people started taking this and taking it in directions that we had no idea that would make sense to do, right? And the things that are closest to this are basically, there's the Stanford Bioinformatics group. They're basically doing some search things for a protein synthesis, and I mean, you can sort of think like genome searches and stuff like that. That's exactly this architecture is very well, set for. Speech recognition stuff. There's the astronomy lab, the search for extraterrestrial intelligence guys. They love this because they're doing these, and I got some examples of that, but doing million-point FFTs, looking for little, sine waves coming from the sky that they can sort of say might be some sort of intelligence out there. Huge amounts of computation. So there's a tremendous list of these things. People doing basically signal processing stuff. Got Microsoft doing some things on it. So lots of different people, and I'll give you a few examples here. So we started building these things. We're actually one thing is they don't cost very much. That's another thing that's kind of interesting, right? We had a workshop not too long ago, and about, 30, 40 people showed up. We're building these things. We've probably built about 30 of them are sort of in process to be built right now, and we'll probably do another run of 20 or so pretty soon. It cost, do I have the price on this one? The price of these things, basically the board's like 4 or 5K, from the assembler. And the chips are another 4 or 5K right now for the chips we're using right now. So 8 or 9, 10K, you get something that's up on the TeraOp performance level, right? Wow. People think, well, FPGA is really expensive. Just normalize it by how much computation you're doing. They're not expensive at all. They're really cheap. And you normalize them by how much power they consume. They're also very, very, very efficient, as I showed you. Okay. So that's what's going on. So here's what people did with them. Now, some people who are so stuck with Von-Neumann-like architectures, right, just can't get away from it. So they take our B architecture, They're trying to figure out how to make a chip that does some sort of, this is a VLIW architecture with, it has, you know, a controller on it, which is, you know, a little ARM processor or something like that. But they actually implement that architecture on the array to sort of solve the software issues, just sort of, so they have something they can, you know, try out. Then when they do the actual chip implementation, it'll run faster, be lower power, probably get another factor of 5 or 10, I agree. But the point is here, you can implement any basic architecture that you want inside these things. That's what the point I want to make. In fact, the difference between what the ASIC did and what they actually implemented wasn't 5 or 10 times. It was only like 2 or 3 times difference in speed between what the ASIC would be with custom design versus what we can get just by programming up this FPGA. This is this ramp project, which I think, you know, I was talking to John Worsnick, the guy I work with closely on this. He's very closely in the ramp project. I'm not so much involved in this. But the excitement that people have in this, it's computer science, you know, people across, you know, architecture research people across the country. The excitement they have about doing this seems out of proportion to, you know, what we're talking about here. We're talking about, you know, putting architectures down in FPGA arrays. We think what's made them so excited about it is, the fact is that we've abstracted away to a large extent that this big chunk of hardware. People knew FPGAs were interesting and could do things, but the problem was they didn't know how to get to them. They didn't want to have to work with this big chunk of hardware that they didn't know how to deal with, right? So I think our abstracting that away is what really has made this very interesting to them. Plus the hardware is not that cheap and we can just give it to them, right? So basically they're talking about doing 1,000 CPU processor emulations on this thing, right? Xilinx gave us $500,000, mostly that's chips. They actually helped us build the boards as well, so it was kind of nice. In NSF, we got NSF money to try to support this thing. So this is kind of getting away from where you think FPGAs can do stuff. So SPICE is a circuit simulator. You know, it solves matrices and stuff like that. Now, the message you do here is you can do exactly what you did on the Von-Neumann machines. You'll use those algorithms, but of course they have problems. They basically are architected for a sequential processor. What you do is you got to look at it again, figure out how you might do it, parallelize it much better, and that's the core of this. I mean, we got to change the way we teach, you know, computer science algorithms in some sense. You can't be teaching, you know, metrics that are associated with a sequential machine. You got to begin to think about how you do it all in parallel and what the right metrics for that are. So that's trying to do SPICE, you know, and this stuff. Radio astronomy applications, I think, particularly interesting. We started that one pretty early. They have been one of our, you know, really strongest. Really worked with us carefully all the way through this because it just solved the problem. They need supercomputer-like performance. I think the next, it's FFTs, pretty simple, straightforward, streaming kind of computation, but lots of it. This is the Allen telescope array, and what he's funded, okay, right, is hundreds of telescopes sitting out in the desert, you know, in the Central Valley there, right? And they do beam forming of these things so they can sort of move around where the beam is and look at certain places with very high, you know, efficiency. Very, you know, they capture all the information from that certain direction, so they get huge, you know, improvements in the sensitivity of the receiver. Huge computation to pull this thing off. This is really supercomputer level performance needed to pull this whole thing off, right? And they looked at, you know, I mean, we're talking like the Hitachi supercomputer or, you know, some of these really big ones. So what they started seeing what they could do with our arrays, right, and started putting this stuff together, and sure enough, we actually have stuff now running out in the desert. Not that big array hasn't been fully built yet, but on smaller ones, they're actually using our boards out there in the field right now to do some of this beamforming and make it happen. This is kind of an interesting picture. This shows the algorithm mapped onto the FPGA array. You see the 2 square holes there. Those are the PowerPCs. Okay, so this chip has 2 PowerPCs. So you can sort of see where the PowerPC size is relative to what the FPGA has there. What you got to think about is when you talk about doing these kinds of algorithms, it's spatial processing. And suppose that, you know, we generally think about doing, you know, programming. You're sequentially sort of organizing the computation you do. Here, it's a spatial processing you're doing. The other thing is, and what our OS supports is, what happens if you stop doing something? You want to do something else. You can reprogram a portion of this chip and have it do something else. So that's basically, it's sort of like, you know, the process call that you might have in a general, you know, standard, you know, Von-Neumann architecture. So there's a mapping here of, you know, time to space that you really have. That's what really allows us to do the parallelism. Because once we go into the space domain, then we can sort of start mapping this stuff across all these various arrays. Yeah?
PowerPC involved in making the reprogramming sort of happen?
Yeah, well, actually, what we do is you can do anything you want with it. It just has a nice little interface into the hardware. So what we do is we go into the PowerPC, and that's what we do is to all the bit files and stuff then come from it. They go out and program up the chip. So that's how we abstracted away some of the hardware by using that PowerPC. Right. So yeah, I mean, it's low-level user interface stuff, just something fine for a Von-Neumann machine, right? That's where it belongs, right? Okay, so here's the last part of it. If you really want energy efficiency, right? If this is, even if we say we got up now a factor of 100 over what you've got from the microprocessors, then there's another factor of 10 or so on the table here that you were throwing away, and that's dedicated. Okay, so you can take basically what our little design flow does is we take that a description of the up at this Simulink level I told you, this MathWorks graphical entry thing, and we map that to an FPGA automatically. I mean, it's direct from there all the way down into the chip. You don't see any VHDL or any of this kind of stuff. That same description, as I told you, is the same one we use in ASICs. So we actually can do an automatic mapping of that same description into an ASIC. So let's say you figure out your algorithm, okay? If you want to get another factor of 10 efficiency, boy, you just make a chip that does it, okay? And boy, you got another, then you are right to the limit of what CMOS can provide at any given time, okay, right? And you'll get faster clock rates and you'll get and better energy efficiency. So a dedicated chip is 10 to 100 times more efficient than FPGA, 100 to 1,000 times more than a processor. So you think the numbers we're talking about are really huge, right? And how we do it, I just described that. We just have our little mapping strategies. So basically, you try to work at that top level. We have all sorts of estimation tools, but it's not so important. I guess the point is that, would people really do this? Is this kind of a crazy idea? Actually, I know people doing some of the biological search problems. They're doing chips to support that stuff because, boy, that's a big, important problem. And if it's a big, important problem, it's worth it to do the chips to do it, right? And so I think, it's something to consider. I mean, it depends on how desperate you are to reduce the power problem. Okay. So, to me, reconfigurable computing is here, right? I mean, there's something really interesting going on in this whole area. The technology, because just has made it viable in ways that we never would have thought about, not too many years ago. And it's going to, and what I think even more importantly is that it's going to get better right with how Moore's law does. I mean, that's what happened to the processors. That was not an architecture that could continue to exploit Moore's law, right? The multi-core is an attempt to sort of do that. But I think just the idea is sort of right, get parallelism, but it just hasn't gone far enough. And this is the way to get the rest of it. We've got a new kind of software engineering, that's for sure. I sort of described that. It's spatial processing. It's going to get away from thinking of these FPGAs as a big chunk of hardware. That's really different story than we've had before. But it's not. We know what we want to get to. It's the environment we've always lived with. Okay. The question is, how do we get there with these arrays as our underlying computational fabric? And I believe over time, all high-performance computing is going to turn to these arrays. I mean, I just cannot see why you'd want to throw 10 to 100 times of efficiency away just for problems of software, which is really probably the main reason it happens right now. Okay, that's it. That's my story. Thank you. Sure.
How do you handle faults?
Faults, I mean, well, how do you handle faults? Okay, so I guess the question is, when you talk about a streaming computing model, okay, it's a little different than thinking about a standard, software model, right? Okay, so what happens is as you go through this, let's say you have some sort of overflow in some of your computation. What you'll do is you'll deal with it locally, okay? It's not a global reset of everything. That's the different thing, because once you have such high parallelism going on here, you've got to deal with these things locally as you go through all this big parallel path. So I think it's a very different way of thinking about how you'll deal with that. Yeah.
I used to work on FPGA mapping and decoders before.
Okay.
The biggest problem that we found was the hardest problem that we found out there was basically partitioning a chip, which is still not solved. Like if you have 100 million elements, you couldn't partition it automatically. You had to do something manually. So that's still a bottleneck.
Yeah. So the point about, okay, now, so how do you really exploit this level of parallelism, and how do you map it onto these arrays? Exactly right. So actually that language I showed you there, one thing you want to do is a hardware idea, which is not a good one to continue in this new world, okay, is that data moves around in sort of lockstep, okay? You don't want to do that. What you want to do is you want to sort of decouple the data movement from the clocks of the FPGA. So you do that through basically asynchronous FIFO-like sort of structures and things like that. So once you do that, then moving from one chip to another becomes transparent because, yeah, there's some delay going there, but if you're not really trying to keep everything in lockstep, then you don't have to worry about it. So I think it's along those lines that you have to solve this problem.
The problem is slightly different. You have a large design. It won't fit on a, like 10 chips. It takes like 100 chips. You have such a big design. And you want to do it automatically. You don't want to do it manually. Like, person doesn't have to come and say, half my program goes on chip 1, and second half goes on chip 2. So that's not a solved problem yet.
Yeah, I agree. So, I mean, the problem is how do you map really big problems across arrays and be efficient about it and not lose. I agree. Not solved. I think there's lots of things that aren't solved here, right? But I think that's probably, don't try to be so efficient. I think that's the other piece of story here. And that's what helps a lot of these problems. Yeah.
I'm just wondering about how the adoption of this will go, because right now, if you look at, say, undergraduate education, students are taught first, write a program that works.
Right.
Come up with a series of steps to solve the problem. Then you profile it, you figure out where the performance bottlenecks are, and an advanced topic is thinking about the motion of data between the various bits of computation. But you've proposed a programming language here where the first thing you got to do is you got to lay out your data motion, and then a secondary thing is you fill in the blocks with what computation is actually done. Do you think it will be difficult to teach people to think in this way about problems?
You've really hit the really important issue here, right? It really is a switch, right? I mean, we are talking about all, as I say, basically algorithm complexity. It's a very different model from what we're talking about here. You almost can not worry about the computational part of it. You got to worry about the data movement, okay? So, and memory access, and that's the issue. I think, well, it's got to start from places like this, right? Who actually can look at this and say, boy, we have a problem to solve, okay? We're going to solve it. We'll build up, what we're trying to do is build up tools to sort of bring new people on board with trying something different. Then I think what happens, academia sooner or later will say, well, geez, all our students are doing this, and why are we teaching this? Okay, maybe we should change. We won't do it quickly because I have those notes, and I don't want to redo those notes again, right? There's a lot of pressure not to change, but I mean, you can do it. It's possible, right?
Back at your slide that you had earlier in the talk with the performance curves for FPGAs and processors, you'll note that things sort of, the slopes sort of equalized about 97, somewhere in there, I think. So this has been kind of the case and isn't likely to change for the last almost 10 years. We'll probably go forward into the future, the relative performance of microprocessors. So why hasn't this happened already? I mean, if this is such a huge win and you can get all this performance gain, what's the problem?
I don't think that actually, I know the slopes you saw there, and I think that actually is a little bit of artifact of just the pieces of data we took right there. You actually get, every time you scale up to new technology, actually what happens right now, the foundries, TSMC, the guys doing the state-of-the-art process, what do they use to drive their next generation technology? It's FPGAs. And why is that? Because they can so easily do a design that exploits the next generation. You scale down by lambda, right, 1.4 or whatever it is, you get 2 times more of those little computational units with no thinking, okay? Then you throw in a little more, you actually get a little bit of extra clock rate. So you actually get, sort of 2 to 3 times more in each generation. The Intel cores, they've stopped being able to increase the clock rate. They cannot increase, it's power limited. And that has really put a lid on them, right?
They're just putting more cores on the chip, so they're playing the same game the FPGA guys are playing, just replicating.
But I say now, what's the right unit to put down? Is the right unit to put down a Von-Neumann core and replicate that, which really has not been designed for the application we're thinking about? Or do you allow yourself to put down exactly what the processing unit needs to be for the application you're interested in?
Well, but the application is running some massive piece of software that's already written, typically.
Ah, there's the problem. There we go. Okay, there's the problem.
People who know how to write that kind of code as opposed to simulating.
So, back to the question you said right there. I think the biggest problem right now, it's training, it's the history. We talked to the.
How is this ever going to become?
I think people are going to solve problems that they couldn't do any other way using this approach, and people are going to look over there and say, "Wow," and they did that. It was cost 100 times cheaper, and it was 100 times less power, and maybe I should do that too. I mean, it could be another company starting up, okay, not named Google, maybe named Frugal, because they want to save money, and basically they will use a very different architecture and a very different approach and won't have the legacy which really keeps people from using this. I think that's a big part of it. So it's the old disruptive technology argument, right? So yeah.
I think you might have shown this, but maybe I missed it. So I see the factor of 1,000 in terms of the efficiency, power efficiency, but what kind of computation rates can you get? Is it roughly the same? I mean,
Yes, I mean
you do that for just a very small amount of computation, you can get 1,000.
The question was, I showed, I was working with efficiency numbers, computation per milliwatt. So the question is, what's the raw computation rate increasing? And if you saw, I think one of those slides I put down there, basically, I mean, these chips are consuming watts. I mean, effectively, we're all power limited, okay? The power PCs are power limited. I mean, the Intel processors are limited maybe at 50 watts, okay? These FPGAs, they're probably limited at 10 watts or something like that. So you're not talking about much power differences there, right? So that's why I say efficiency is the whole name of the game, because you're really power limited now, right? So, any other questions? Yeah.
So the thing is, when you start with trying to solve the power problem, so does the language actually have explicit construct to say that this part of the chip actually takes this much power, so scale up the voltage or scale down the frequency?
Yeah, well, so let's go after, if we're really after power, maybe we should be a little bit smarter about how we do the FPGA design, the chip design itself. That is, I think, really another big, huge factor. Like I said, Xilinx and Altera, when they designed these things, they just didn't think about this problem. They didn't really worry about power for the longest time. Right now, they're just beginning to deal with the power issues. It's like processors, 10, 15 years ago. People did not care about power 10 15 years ago. Now, all they care about. The FPGAs are in the same word, except now they're just beginning to hit this issue. And I think there is a lot of stuff you can do. All right, so, yeah. No problem.
There's sort of a fundamental physics problem though with that, which is that to be reconfigurable, you have to run your wires to a lot more places than you would if you weren't reconfigurable. And that's where all the power goes, is charging and discharging the capacities of that wire. So it's unclear to me that there's going to be any big win to be had.
Okay. That's, again, part of the programming model here. Okay, so if you really think about stream programming and basically locality of computation and memory access, right? Yeah, the original FPGA idea is you put down this big chunk of random logic and you can program it up any way you want. You notice how that example I showed you of that SETI, that spectrum analyzer for the radio astronomy guys. The computation, the colors there were showing where the computation was. You don't spray that stuff all over the chip. You locally basically control it. In fact, the way we do the mapping to make this thing so it's fast and solve, I'm sure you know some of the problems of mapping into big FPGAs, you don't just go in there and just flatten this whole thing and just start placing around it. What you do is you go in with blocks that you've basically pre-compiled, place those down, which have all the local interconnects sort of taken care of in the best possible way, then you put those blocks together. Yeah, you lose stuff between all these things. That's okay, because you don't have to be so efficient. The old model was, Xilinx designed their chips right now so you can route those things 100%. That is just crazy. You do not need to do that, right, if you're trying to do this kind of application. And that is some of the cost of those chips and some of the power wasted because they've designed these things to be 100%. Even with that happening, these things are still winning big time against any other kind of architecture, right? So, yeah.
I think functional programming is related to this. Is that the model for programming influence?
Yes. Well, there's functional programming. I think it's along those lines, exactly the sort of the programming model that you really need to think of here. So, applicative programming, functional programming. I think it's those kinds of programming models that make sense. I think you don't have to get too weird, though. I mean, you can start off just, you can see, blocks. If you can organize your architecture into stream-like blocks and put blocks and handle the communications up front, make blocks fairly big that may use some string compare or some things like that, right? And just do that really well. So it's kind of a functional programming-like idea, right? And then you can program these things, and I think fairly efficiently, right? And deal with sort of the non-automatically, but the mapping issues right now to put these things on huge arrays. You must be doing some very close mapping right now onto your machines, I would guess, right? I mean, you're not letting that just some compiler figure all that out. You must be taking control of that yourself. I think the same thing's going to happen here for the time being until we really have much better tools, right? So, yeah.
One of your slides, it showed that a rack of your stuff could get about 1.5 teraflops.
Yes.
I know that scientists love double precision floating point numbers, and they also like to do intensive things like Fourier transforms or discrete transforms. So what's the kind of performance loss?
That 1.5 teraflops was double precision floating point modules, not optimized for the FPGA. We actually just took some code, some RTL code, and just programmed it on there. I think if you could go in there and if you wanted to even improve a lot better, right, you could do sort of more efficient versions of these floating point units and even do better than that number. So the answer is it's very good. That's the number. This thing does floating point. That's the thing about it. Geez, doing floating point on an FPGA, when we started putting those numbers in, we thought, could you really do it? You know, and you go back 5 or 6 years ago, you'd put 1 per chip. Now you put 50 or something like that per chip or something like that, right? So, any other questions? Okay. Well, thanks a lot.